This one, you have three carbonyl containing molecules reacting with sodium borohydride. So to solve this question, you gotta remember what sodium borohydride can do. It can react with the carbonyl, but only the reactive ones. Ketone, fine. Aldehydes, okay, but not the ester. So this is an aldehyde. Sodium borohydride can easily reduce that one by delivering the hydride. Electron pair is going to go up. And then sodium borohydride, you normally carry out the reaction in the source of the proton, like water or the alcohol. So it just pick up the proton immediately. It doesn't wait until the end, unlike the lithium aluminum hydride. So when this delivered, this get a oxide and pick up from the solvent, you get the range there. So aldehyde, no trouble. What you see here, that's a ketone, right? Ketone also react with the sodium borohydride. It delivered, you get an alcohol there. But what about this one? That is an ester, right? Ester is a valuable substrate of the sodium borohydride, so it doesn't do that. So what you get the ester to remain intact. So that is going to be the answer. So it's pretty simple, right? If the same question, I ask you to draw the products of the lithium aluminum hydride treatment, then you know the aldehyde is going to be reduced, ketone is going to be reduced the same way. But they're not going to be alcohol immediately because the lithium aluminum hydride, we have to wait until the end for the adding water, because the water will kill the reagent immediately. So that's the reason it's going to stay alkoxide until the end. But what about that one, ester? It's not going to be reactive with the lithium aluminum hydride. Lithium aluminum hydride is so powerful, it really doesn't care what carbonyl it is. It's going to go for it. That makes an alkoxide, but that has a leaving group. That's the what makes the differences between the ester and the ketones. This will make the carbonyl back, kicking these methoxy groups out. That makes an aldehyde. Aldehyde is definitely get reduced by the lithium aluminum hydride to becomes a primary alcohol. All of these alkoxides stays like this until the end. When you add the water as a walk-up step, all three oxygen will pick up the proton and becomes alcohol. So they have a different reactivity. And then like an ester, it's not going to consume just one hydride. It'll reacting further again until there's no limit groups there. So this is something that you really have to remember that. So that's pretty simple. I would say it's a simple question. What about this one? This is what we ask a lot. Because there's a way to make a mistake. And we always see the mistake made by students. So a lot. So that's why we love this question. We like to lure you to trap so you just spell down, and then the person grading is laughing about religion. We are a mean person, sorry. All right, so let's say what will happen when you're treating this thing with a lithium aluminum hydride. Lithium aluminum hydride, as I talked about, it doesn't care any carbonyl, it just goes for it. Aluminum hydride, silicon aldehyde, sure, let's go for it. It'll make an alkoxide, right? By delivering that. What about this carbonyl? That's a carbonyl of an ester, right? So lithium aluminum hydride is no trouble. Sodium borohydride wouldn't touch that. But lithium aluminum hydride, it'll go for it. So it makes an attack, alkoxide goes. But the thing is, it's a cyclic ester. That's the trick. That's what makes it tricky. You have to keep track of the words bound to. And then I will show you that your answer should show the alkoxy groups that we typically don't care about the other ones. So these ones are initially formed. Hydrogens makes an attack. You get that as an alkoxide, but that's a leaving groups there. When this will come back make a carbonyl, this will come up. So far, That's the aldehyde we produce. We never care about ester part, this part leaving out, because that's a normally like a methoxide, small alkoxide going away. We don't care. But this alkoxide is tethered to the main chain, so they never go away. So you should place it. You should keep it in the structure of the product. That's the what out of many people make a mistake. They just kicks it away, and then they just thought that this thing's gone. No, it's not gone because they're connected still. That's what makes it, like a trap, very easy trap. So I'm luring you in. Sure, ester will react with the lithium hydride, but alcohol part of ester normally they kick away. But this cyclic ester, you shouldn't kick it away because they're still bound. So these are toxic groups. It's coming from this alcohol side of ester, that side. Still make a bond, still there. Aldehyde, not going to say, it's going to be reacting further because the lithium hydride and aldehyde is an automatic reduction because so much reactive for the aldehyde. It's going to go for it, another alkoxide. All three of them still there until you add the water. All get the protein in the end, you get an alcohol. So this becomes an alcohol, that becomes an alcohol, but that alcohol, that's the one that you should place. You should keep it. That's the one people sometimes easily forget. Because they're happy to have this reaction done, alkoxy groups, sure, that goes away. Not in this case. We ask these questions a lot. So I want you to. So that's why we are laughing when we miss this. All right, so this is the same question that you should also worry about the Grignard too. This is not just reduction of the lithium hydride. If that's a Grignard, Grignard makes an attack to the ester, right? And then you got a toxic groups there, you gotta show that because that never goes away.